This is problem 421. It's on page 175. Nitrogen gas at 60 kilopascals and 7 degrees Celsius enters an adiabatic diffuser steadily with a velocity of 200 meters per second, leaves at 85 kilopascals, 22 degrees Celsius. Determine A, the exit velocity of the nitrogen, and B, the ratio of the inlet to exit area. So let's make a sketch. Now this is a diffuser. Now a diffuser, I usually draw my flows from left to right, and so a diffuser opens up basically. Now the system that we take is the area or the volume, I should say, inside of the diffuser. And usually these things are basically revolved around a central axis. So air is flowing through this diffuser. It flows in at what I will call section 1 and flows out at what I will call section 2. Now remember, when we're dealing with this type of device, we're usually assuming that it operates at steady state. So there's no accumulation or depletion of mass or energy within the control volume. So whatever mass and energy flows in has to flow out. So they have to flow in and out at the same rate. So, and I put air here, I'm sorry, it should be nitrogen. Let's try that. So the nitrogen comes in at a pressure at state 1 of 60 kilopascals and leaves at a pressure of 85 kilopascals. It comes in at a temperature of 7 degrees Celsius and leaves at a temperature of 22 degrees Celsius. It comes in with a velocity of 200 meters per second, and we're supposed to find the exit velocity. Now, anytime you're working a Chapter 4 problem, really anytime in the course, but especially Chapter 4, you should be thinking about, well, where's the energy? Where's it going? How's it changing forms? Okay, so when you see temperature, what form of energy do you think of? Good job. Now, when you first came into this class, when I told you temperature is a form of energy, you'd have probably said, oh yeah, that's heat. See, so you've already changed. That's good. Temperature indicates thermal energy. Now, what's thermal energy again? It's just microscopic kinetic energy, basically, right? It's just molecules moving around on the molecular scale. Okay, maybe they're rotating, translating, vibrating, whatever. It's thermal energy, right? So that's what temperature makes me think of. So it makes me think of a U, basically, right? T makes me think of U, internal energy. What's that? How sweet, I didn't know you were thinking of me. Okay. What about velocity? What form of energy does that make you think of? Kinetic. You've been studying physics and things long enough. When you see velocity, you think, oh, okay, 1/2 mv squared. Kinetic energy. Fine. You're right. Velocity makes you think of kinetic energy. So let's just say Ke. Okay? What about pressure? What form of energy does that make you think of?
Force.
Force is not energy, right? Force times distance is energy, so it couldn't be force. What form of energy would it make you think of? It doesn't. Most people say potential energy, okay? Because they think of force or they think of the pressure being compressed like a spring, which is like force. I got to break that somehow because that's not right. Pressure is a side effect of thermal energy. Okay, if you had a bunch of gas molecules in a container and you take the temperature way down, what happens to the pressure? It drops also. So that pressure is just a side effect. Here's what I want you to think of. When you see pressure, I want you to begin to think of flow energy. So how would we write flow energy? I don't know, but let's just do it this way. When you see temperature and pressure together, I want you to think of enthalpy. Because enthalpy includes internal energy and flow energy. I guess I could write this as PV, but that would just confuse the issue because we've already got a V here. Well, Q we use for heat transfer, so that doesn't work either. It's a good idea, but here's what you really need to think of. When you see pressure and temperature together, you need to think enthalpy, because that would quantify the enthalpy in the stream. Okay? So basically we have a certain amount of enthalpy coming in and a different amount of enthalpy leaving. Now here's what you're going to be surprised about. The pressure will not make one bit of difference in our energy balance calculation. That seems strange, doesn't it? But for an ideal gas like nitrogen or air, remember Joule's experiment showed that the energy in that air depending only on its temperature, not on its pressure. Okay?
That's a side
And it's a side effect. Pressure is a side effect of thermal energy. All right, so we want to determine the exit velocity of air, and basically we've been dancing around this. We need an energy balance, right? We need to account for how much energy comes in, because that same amount of energy has to leave, but it'll be in a different form. So that's how we can calculate the exit velocity. So what would the energy balance look like that I should write down here? Well, we had it in the slides, right? How did it go?
H2 plus velocity 2 squared over 2
Equals?
equals all that with ones.
With ones. All that with ones. Good job. Same thing, right? It just says that nozzles and diffusers mix up enthalpy and kinetic energy. That's all they really do. Change from one form to the other. Now, most of the time, we will neglect the kinetic energy at the exit of the diffuser. Now, if we neglect it in this problem, we'll be crossing off the very thing we're looking for, right? So we probably shouldn't do that. But most of the time with a diffuser, we cross off that v squared over 2 term for the exit because it would be small, it wouldn't matter, okay? Since we can't do that, let's solve for it. So the velocity at the exit would be equal to, well, let's see, we've got to subtract off h2, so h1 less h2, bless you. We have to multiply by 2, and don't forget we've got a v1 squared here, and then take the square root. So I just solved it all in one step. All I did is rearrange the equation for v2. You can verify that it's correct if you want with algebra. Okay? Now I thought we were going to have temperature in this thing. I don't see temperature. I see enthalpy, but I don't see temperature.
Well,
Enthalpy includes temperature.
Enthalpy, yeah, there's a way of approximating it, right? A change in enthalpy can be approximated as Cp delta T. Let's write both of the equations again just for practice, okay? Delta U is approximately Cv delta T. Of course, delta H is Cp delta T. I'm trying to build a bridge in your mind between Cp and H and Cv and U. So let's write that again just for practice. I try to get you guys to write it 10 or 20 times throughout the course. Basically, Cp goes with H, Cv goes with U. So how can we use this?
do we know our
Well,
temperature change?
exactly, yeah. I see a delta H here. Couldn't I approximate that as Cp delta T? Sure. Yes, you can. What would it look like? 2 Cp T1 less T2 plus V1 squared. It's easy. Well, basically, we need the heat capacity of nitrogen now. Okay, we should be able to get that. If you look up the heat capacity of nitrogen, what you'll find is that its heat capacity is pretty close to the heat capacity of air. Why would that be the case?
Air's like
Air's almost all nitrogen, right? So it makes sense. So square root of 2, the heat capacity of nitrogen. Do you see that in your book? It's in the first appendix.
It's 1.039.
Good. What page did you find that on?
8.3.
843. 1.039 kilojoules per kilogram per Kelvin. That's the heat capacity, Cp, of the nitrogen. T1 less T2 would be 7 degrees Celsius less 22. I'll put the temperature units out here. Now, the degrees Celsius I'm crossing off with Kelvin. How come I can do that? Because it's changed, right? Both of these are changes. So that works. Now let's not forget we need plus V1 squared. Now V1 is 200 meters per second squared. Can we just throw all of this into our calculator? Well, wait a second. We got kilojoules per kilogram here and meters squared per second squared. We can't just put those two things together, right? You can't add apples and oranges. Those are measuring the same dimension, but in different units. Look in the front of your book. Look at the first inside cover of your book and look for energy. Under the energy area, do you see specific energy, kilojoules per kilogram?
Yes.
How many meters squared per second squared are there in 1 kilojoule per kilogram?
1,000.
There are 1,000. You see that? If you're using highlighters, you probably ought to highlight that one because that one's going to be really useful in all of your nozzle and diffuser problems. You could even write in the back of chapter 4 that 1 kilojoule per kilogram is 1,000 meters squared per second squared, because that's where you'll use it most of the time. Now, what about in English units? What would the units be of specific energy in English units? Pounds mass instead of kilograms, good. How about instead of kilojoules, we'd use BTUs. So it'd be BTUs per pound mass. How about velocity squared? What would the units usually be in English units? Feet squared per second squared. So we'd have the same problem in English units. Is there another conversion factor to go from BTUs per pound mass to feet squared per second squared? Look on the inside cover of your book. Do you see the number? What is it?
25,037.
25,037. You probably want to highlight that one too and copy it down to the back of chapter 4 as well. So that should also be under the specific energy area near where you found the other conversion factor. Those are really important and very useful. Now, do I want to multiply by 1,000 or divide by 1,000?
Divide by.
Well, I think I want to multiply by it because look, there's 1,000 meters squared per second squared for each 1 kilojoule per kilogram, right? That way I get rid of the kilojoules per kilogram in the first term, and I have all meters squared per second squared, so that when I take the square root, I get meters per second.
Oh, okay, okay.
That's all right. I don't want, I mean, is square root kilojoule per kilogram a valid unit for the dimension of velocity? Sure. I mean, I don't know that you'd want to change out your speedometer in your car for square root of kilojoules per kilogram, but you could, or square root of BTUs per pound mass. It's not something we use commonly, right? So anyway, plug all this in and you'll find that the velocity at the exit, let's see, V2 comes out to about 93.97 meters per second. Now look at this. The kinetic energy obviously decreased, right? So where did it go?
Heated it up.
Heated it up, right? Another way of saying that is it went into thermal energy and flow energy. Okay? That's basically all this equation says. It says you can move back and forth between kinetic energy and thermal/flow energy. Now that wasn't the only question. Notice we've used the energy balance, but that wasn't the only question. The other question was, what's the ratio of the area at the inlet and the exit? It's really common that if you've used up the energy balance, you have to use the mass balance. So let's see what we can do with the mass balance. The mass flow rate coming in must be equal to the mass flow rate leaving. That looks pretty boring and pretty useless, right? But is there some usefulness here? Actually, there is. There's another way of writing mass flow rate. You could write mass flow rate like this. The density of the incoming stream multiplied by the velocity of the incoming stream multiplied by the area of the incoming stream. Because notice, the velocity times area, this is the volume flow rate. When you multiply that by the density, you get the mass flow rate. So this is just m dot 1 equals m dot 2 rho 2 v2 a2. These are the same equation. They're just written differently, that's all. Okay. Now, why does this equation look useful now? Well, it's got two areas in here, which I can rearrange to solve for the area ratio that's requested. So when you do that, a2 over a1, well, let's see, we'd have to write that as rho 1 v1 over rho 2 v2, right? Now we know the velocities at the entrance and the exit, but do we know the density? Not yet. Now what do you know about nitrogen?
These velocity.
These are velocities, yes. I try to make a script V for my velocities. What do you know about nitrogen? I heard it a second ago. Maybe more dense there, I'm not sure.
It's very similar.
It's an ideal gas, right? It's going to behave ideally. Did I give you guys the equation for calculating the density of an ideal gas from
Yes.
the ideal gas law? How did that go?
Density equals P over RT.
P over RT. That's the way I remember it. I kind of cheat. I know that the rho looks a lot like the P, so I just write those two and then I divide by RT and I'm done. Okay. But there's the density. So we could plug in for rho, we could plug in P1 over R over T1. And for rho 2, P2 over R over T2. Right? Now notice that the gas constants R will cancel. We don't even have to look it up. Whoops, there's my eraser. Better not make any more mistakes. So P1 over P2, let's put all the common stuff together. So let's put P1 with P2 Let's put T2 with T1, that would look like this. If I invert the fraction and pull it out. And then V1 with V2. Okay? So now I've got a bunch of things I already know that I can just plug in here. All right, great, let's do it. Let's see, P1, no problem, that's 85 kilopascals. I'm not gonna put in the units, you can see that all the units are gonna cancel, right? So as long as I'm consistent, I should be okay. 85 kilopascals over 60. The temperature at the exit is 22. The temperature at the entrance is 7. And the velocities, let's see,
P1 over
P1.
P2?
Yeah,
What's that?
P1 over P2?
P1 over P2?
or P2 over P1.
It's P1 over P2, that's actually correct.
So
And then
60
this
over
T2 in the denominator goes to the numerator.
You can't really-
60 over
You
85.
swap.
Did I switch it?
Yeah.
P1, thanks. 60 over 85. See any other mistakes? No? I see one, but let's see if you can find it. Okay, so V1 is 200, V2 is 93.97. Now, if you plug all this in your calculator, you'll get the wrong answer. You know why?
What is temperature in currently?
Temperature is in degrees Celsius.
Do we need to change that to Kelvin?
Do we need to change it, Kelvin? Good question. What law did we invoke?
Yeah,
The ideal gas law. Remember, the ideal gas law has to have absolute pressures and absolute temperatures, okay? So I still don't have to pick up the eraser because I left myself some space on purpose. Okay, 273 has to be added to both of those, otherwise we won't get the right answer. You should try it. Take 22 over 7 in your calculator, compare that to 22 plus 273 over 7 plus 273. You will get a different ratio, right? That's sort of anticlimactic, but the area ratio, well, it's even worse because over here I've solved for A2 over A1, but in my notes I've actually written down A1 over A2, so what I really have is the inverse of whatever this result is. A1 over A2 comes out to about 0.6318. If you were to calculate this, you should just get the inverse of 0.6318. Yeah, so if you invert it, do you get this? 0.58 inverted?
0.60, yeah.
Yeah, 6318. Okay. So there are the answers that we were requested to find. How did I find these two things? I applied a mass balance and an energy balance. Most of the time, the energy balance will be more valuable than the mass balance. It will give you more information or get you closer to the solution, or you have to use it first. Pardon me, but I would recommend you write down both. Any questions?